Hi everyone, welcome back. In this particular video, we're going to start talking about acetal hydrolysis. In a previous video, we've looked at this formation of an acetal. An acetal is formed when a carbonyl compound, now I've used the specific example of acetone here, but you want to read this as a representative of a carbonyl compound. So when you react a carbonyl compound with alcohol, in presence of an acid, you make what's called the acetal. And when this reaction happens during the acetal formation, you lose a molecule of water. And this is key because this reaction is reversible, which is depicted by the arrows here. So the loss of this water molecule is crucial because one way that you can actually push this reaction forward to the product to make more of the acetal or to favor acetal formation under these conditions is to remove water. Okay, so you could remove water to favor the forward reaction. Just Le Chatelier's principle. Okay, so once you remove one of the products that's formed, the reaction will be pushed forward. Okay, now what we're going to do in this video is focus on the reverse of this reaction, which is the acetal hydrolysis. So the hydrolysis of the acetal is achieved by using aqueous acid, which we're going to represent by H3O+. Now, remember that a hydronium ion, whenever this is shown, this basically means you have an acid, you have water around. And that's what we need for this reaction to go back, because to favor the acetal formation, if we will remove water, then to push the reaction backwards, we should have more water. Because if you load up on the amount of water here, then the reaction would be pushed backwards. But we're going to look at it as if we are going in the forward direction from the acetal to the carbonyl compound. Okay, so the acetal to the carbonyl compound. So the reaction is facilitated under aqueous, using an aqueous acid, water plus some acid that would push the reaction forward. Let's look at the mechanism of this acetal hydrolysis. So now the mechanism has a lot in common with the forward reaction. All you're doing is doing the same steps, but now in reverse. Okay, so we'll start with the acetal here. So let's say we have the acetal molecule, and under acidic conditions in presence of acid, one of the first steps that can happen between these two, the acetal and the acid, is a protonation. Now we've seen this like several times. Whenever you have a molecule which has like lone pairs on it, it can get protonated. So one of these oxygens, doesn't matter which one, can pick up a proton from the acid and it will get protonated. And it will give us the protonated acetal, where one of these oxygens is protonated, plus water. Now, if you sort of keep your eye on the target, notice what we're trying to do is we want to make the carbonyl compound. So we have to get rid of both of these OR groups, and we need an oxygen that's going to be double bonded to that carbon. Okay, so we have to get rid of both OR groups. Now, similar to a hydroxide, these are bad leaving groups. So one way to get rid of them would be to protonate them so that they become good leaving groups. And then it should be easy to push them out. Okay, so that's what we did here. One of the OR groups is now protonated. That would make it a better leaving group. And so what can happen now is the other oxygen can use its lone pairs to form a double bond with this carbon, and the alcohol would get kicked out. So that group gets kicked out. Now again, all of these steps are reversible. So we'll get this plus a positive charge. Now if you look at the mechanism of the acetal formation, we had a very similar, we had a similar species there, okay? That species was there. And plus, you're going to make ROH. We get the alcohol out. Now, if this alcohol goes and attacks this carbonyl carbon, the double bond would open up and we are going forward then, okay? But in this particular case, we are moving forward. We are going forward to the carbonyl compound. Sorry, we were moving backward if it attacks. Now we are moving forward here to the carbonyl compound. Now from here, again, this reaction is happening under aqueous acidic conditions. There is a lot of water around. So a molecule of water can come and attack this carbon. And like I said, this oxygen from the alcohol can also go and attack. But if this oxygen goes and attacks that carbon atom, we are on our way back. But when the water molecule comes and attacks, that's what takes it forward. And statistically, there's more water around, so the chances of a water molecule coming and attacking it is much higher, the probability of that happening, okay? So this would attack, the double bond opens up. So that means we get to this new intermediate where we have the water molecule connected to it, and then we have an OR. Now again, if you try to compare this structure to our product, looks like this oxygen is what would make that double bond, okay? That's what we need. So we need to get rid of those hydrogens, and we need to get rid of this OR group as an alcohol again. But it's all step by step. So in the next step, another molecule of water can come in and deprotonate this. So we got rid of one of the hydrogens there to get, I'm sorry, I added an R group here. These are not there. Okay. So we get to the intermediate here. That, and plus we have the hydronium ion. So along with this, we have the hydronium ion that formed, okay? Now, again, look at that intermediate, very familiar. We've seen it in the forward direction. This intermediate is the hemiacetal. Okay, that's the hemiacetal. Okay, now from here, we need to lose this OR group to get to the carbonyl compound. So moving forward, what's going to happen is that oxygen will come pick up a proton. Now, again, with all of these steps, what's important to remember is it does not have to be this oxygen. That oxygen could get protonated, but if that oxygen gets protonated, we are going back, okay? So that's why these steps are all in equilibrium. So whenever this oxygen gets protonated, that will move us forward. So we'll get this, one lone pair, positive charge, and plus we will get water. Okay, so that OR group is now protonated. That would convert it into a good leaving group. And so now the hydroxyl group can help push that out. That would provide the lone pairs to make a double bond. So as you can see, now we are approaching our product because now we've got the double bond O with the hydrogen on it, one lone pair, one positive charge, plus we've got alcohol here that came down. And now we are really close. One last step where another water molecule helps deprotonate that intermediate so that we get our carbonyl compound plus acid. And again, notice similar to what we've been seeing in some of the recent mechanisms that we've been looking at, this acid is only catalytic. That's sort of shown by the square brackets, okay? You only need a catalytic amount of acid because when you start this process, the mechanism starts, you consume a molecule of acid, but by the end of it, you've actually regenerated that acid. So this process can go in cycles right now, okay? So only a catalytic amount of acid is needed. So that's the mechanism of an acetal hydrolysis. Now, the fact that an acetal can be synthesized, okay, or a carbonyl compound can be converted into an acetal, and an acetal can be converted back to the carbonyl compound, offers some advantages that allows us to actually use acetals as protecting groups for carbonyl compounds. I'm going to demonstrate that here using two examples. Okay, so we are going to continue here, and I'm going to demonstrate how the acetal formation reaction can be used profitably in organic synthesis. Okay, you can actually use acetals as protecting groups for carbonyl compounds. What would be some examples or like some scenarios where this would come in handy? Let's look at an example or two. Okay, we'll look at two examples here. So let's say we have a carbonyl compound where we have a ketone. It's a dicarbonyl compound now. We'll call this a ketoaldehyde. Okay, we call this a ketoaldehyde. It has both a keto functional group and an aldehyde functional group. And what we want to do is convert this ketoaldehyde into that compound, which is a hydroxy aldehyde. Now, we can come up with a very specific name for it. It's actually a beta hydroxy aldehyde here, okay? We will learn other reactions later that would help us make these molecules. But right now, what we're doing is we're just trying to convert this ketoaldehyde into this beta hydroxyaldehyde. And if you compare the two structures, what you notice is in going from this reactant to the product, the keto group is reduced, but the aldehyde group is not, okay? One of them is retained, the other one is reduced. So what sort of reagents can we use to reduce a keto group? And good examples are sodium borohydride, lithium aluminumhydride, right? So we can use sodium borohydride or lithium aluminum hydride. These are both reagents that help reduce ketones to alcohols, secondary alcohols. But wouldn't these also reduce the aldehyde to a primary alcohol? That would happen, right? So we have to somehow do a reduction here such that only the ketone is reduced, but the aldehyde is not. How do we do it? Now, this is where the acetal functional group comes in, or the protecting ability of acetals comes in. If I take this ketoaldehyde and if I react this with a diol, now a specific molecule here. So I'm going to react it with some acid. We've talked about para-toluene sulfonic acid before. That's a very classic example of an acid, an organic acid that's used for catalyzing these reactions. So if I take this ketoaldehyde, react it with para-toluene sulfonic acid and ethylene glycol, okay? This molecule here is ethylene glycol. if we do that, this glycol has two hydroxyl groups in it. It should be able to make an acetal with the carbonyl groups. But notice how we have a ketone and an aldehyde, and the aldehyde group is actually more reactive than a keto group. And we've talked about this before. Because of steric and electronic reasons, aldehydes react faster than ketones when you're doing nucleophilic addition reactions. So what would happen here is we will be able to selectively protect, you'll be able to selectively protect this aldehyde functional group while the ketone is retained. Okay, that would not undergo the acetal formation reaction. So we can selectively protect the keto group. Selectively protect the aldehyde group because the aldehyde is more reactive. And now once you've done this protection, there is no aldehyde, there's no more, right? And so now if we do a sodium borohydride reduction on this molecule here, let's say we do this in methanol, okay, a sodium borohydride reduction, or you can do it actually in lithium aluminum hydride. That may be a better reagent, and I'll explain why actually for doing this reaction. So we can do the reduction using lithium aluminum hydride. So let's do lithium aluminum hydride using THF as a solvent. And whenever you do a lithium aluminum hydride reaction, you do it in THF or diethyl ether as a solvent, and you follow it up with an acidic hydrolysis. Okay. Now, when you do this, the lithium aluminum hydride is going to go reduce the ketone to the alkoxide. But there is no aldehyde, so it cannot reduce it. And then the alkoxide gets protonated. But under these similar conditions, the acetal could also ring open, right? So if we do this hydrolysis with a little bit of heat, like when you're doing the workup, like we add some heat to it, what it would do is it would actually bring us to the product that we want, the aldehyde. We'll get the alcohol and we'll get the aldehyde. So this hydride from here will attack only the ketone. And then when you're trying to do the workup, that workup step would also serve to basically reverse the acetal formation so that we get the aldehyde back and we've made the product here. Okay, so that's one example where you can use acetals as protecting groups for aldehydes in presence of ketones, and because of the difference in reactivity of aldehydes and ketones. Because that's one example. Now, let's look at another example quickly. And here we'll use a different functional group, not necessarily two carbonyl compounds, different functional groups. So let's say we have a second example of a molecule where we have a keto group and an ester group in the same molecule. And what we want to do is we want to convert this keto group into the, not the keto group. We want to retain the keto group, but convert this ester into a primary alcohol. Okay, so esters can be converted into primary alcohols using lithium aluminum hydride. Okay, so again, we have a keto group and an ester group. So in this particular case, if we did an acetal protection, again, ethylene glycol is a very standard diol that's used for doing these acetal protections or protections of carbonyl groups. Okay, now in this particular case, there's only one carbonyl group, This is not a carbonyl functional group. That's a carboxylic acid derivative that would not undergo this reaction. So the carbonyl group, which is the ketone, would undergo a protection. And from here, we can do a reduction with lithium aluminum hydride in THF and follow that up with an acidic workup. The lithium aluminum hydride converts the ester into the primary alcohol. We'll look at the mechanism of that reaction in a different video. It would convert the ester into a primary alcohol, and then the acidic workup here would put the hydrogen, would protonate the alkoxide that's formed, and simultaneously deprotect this acetal. And so our product here is going to be what we want. It will give us this keto alcohol as our product. So we can use the acetal protecting group or the acetal as a protecting group to do some chemical reactions, to selectively do reactions on certain functional groups in presence of other functional groups. Okay. So I hope you find that video useful. We've talked about the acetal deprotection, and then we followed up with some examples of examples where an acetal can be used as a protecting group for carbonyl compounds.